In this video, we're going to take a look at some interesting disaccharides. And in a previous video, we took a look at monosaccharides, disaccharides, oligosaccharides, polysaccharides. But now we know just enough organic and biochemistry to make it a little bit interesting. So here I have two glucose molecules. This one here is alpha D-glucose. Alpha because this hydroxyl group is in the down position. This one over here is just D-glucose, and that's because this hydroxyl group, it could be up, it could be down, it doesn't matter. And I'll explain why here in just a quick second here. Now, if we were to join these two together, where they tend to join is between the first carbon atom here and the fourth carbon atom there. So I'm just going to number these really quick here. So here's 1, 2, 3, 4, 5, 6 carbon atoms. And then over here, 1, 2, 3, 4, 5, 6, like that. And this becomes important in how we name this molecule. So two glucose molecules, we're going to join them together. And you look at this right here and you go, okay, all right, I've seen this before. Hydroxyl groups, right? We're going to remove water and we're going to join them together. And you'd be right. So I'm just going to remove these two groups like this, and then I'm going to join them together. And so when I join them together, it's going to look like this, okay, like that. And I've removed water, so I'm just going to add HOH over here like this. And we have a fancy name for this here. We call this a glycosidic linkage. And this one here has a name. It's called 1,4, and it's alpha, and that's because it's going down like this. So we call this an alpha 1-4, alpha 1-4 glycosidic linkage. Okay, so I'm just going to glycosidic linkage. So it's an alpha 1-4 glycosidic linkage right here like this. Now, what makes this interesting is this particular molecule here, two glucose molecules joined like this, has a fancy name. It's called maltose. And you might recognize here, okay, we've got that OSE ending that tells us it's a carbohydrate, or it's a sugar of some sort. And maltose, you might recognize that name, that's the sugar that's present when we take barley, we break it down a little bit, and it's added to ice cream, and then it's mixed together to make a malted, or a malt. And there's a great place in Duluth called the Malt Shop down on Superior Street, one of the best places to get malts. Now, I left this hydroxyl group here just like this for a reason. And the reason is this could be in the up position like this. So if it was in the up position like that, then this becomes beta. Okay? And if it was down, it becomes alpha. All right? And it actually exists in equilibrium. And that is to say that this hydroxyl group is flipping back and forth. And you say, well, wait a minute, what about these other ones? Do they do that? They tend not to. They tend to be locked in place. And what allows this to flip back and forth is because this carbon ring here, it can open up right here. And so if I were to just open it up briefly, we would end up with an OH like this. And then here we have our carbon double bond O like this, our aldehyde group. And you might be able to picture this as being like the Fisher projection, where here would be the top aldehyde group, and then we would have our chiral carbon atoms with the hydroxyl groups on there, and then over here at the bottom, okay? And so the reason I bring this up is there's an aldehyde group here in equilibrium with the alpha and beta form. And that means with the aldehyde group, this sugar here, this disaccharide, is a reducing sugar. Okay, so this is a reducing sugar just because that there would be present. This disaccharide is also interesting, and we'll get to the name in just a second here, but just a little review. here we have a glycosidic linkage going in the beta position. And so this one here is beta 1,4, beta 1,4. So this is the first carbon atom, 1, 2, 3, 4, 5, 6. And then over here we've got 1, 2, 3, 4, 5, 6. So this is beta 1,4 glycosidic linkage. And this monomer right here is glucose, and this one over here is glucose. Now, together, if we join these two together, this has a fancy name. It's called cellobiose. And cellobiose, you may remember, is the disaccharide that if we string a bunch of these together and make a polysaccharide, this is what is the structural carbohydrate in plants. And this is something humans don't break down, right? This is the fibrous material in plants. Now, cellobiose is very interesting in that, okay, we can't break it down. You can chew it all you want, right? It's just fiber, it's just roughage. But if we were to change this hydroxyl group right here, just change it to the up position. If I just go like this, it becomes a different molecule. Now, instead of being glucose, it becomes galactose. Just a different name here. Becomes galactose, and then we change over here. This becomes something different. This becomes a completely different disaccharide, and this one is called lactose. Lactose. And lactose, you might go, oh, wait a minute, I've heard of that before. Yeah, lactose is the sugar that's found in milk. And there's a lot of people that don't have the enzyme to break this down. And so the enzyme to break down lactose is lactase. Now, ASE ending in biochemistry tells us that that's an enzyme. And there's a couple ways of looking at this. One, you could say people are lactose intolerant, or you could say that they're lactose persistent. And you're like, well, what the heck is the difference? Well, here's the thing. 60% of the world's population doesn't drink milk into adulthood. 60%. So if you drink milk and you're an adult, you're in the minority. So should we say that everybody else is intolerant, or should we say that you are persistent? I don't know, potato, potato. But it also raises another question. Why are some people lactose intolerant and not others? Well, it turns out the people that produce this enzyme into adulthood generally are Scandinavian or Northern European descent. In the rest of the world, not so much. So the people that are lactose intolerant tend to be African, Mediterranean, Native American, Southeast Asian, or a lot of Asia, Southeast Asian, are lactose intolerant. And okay, why? Why is that? Well, there's a couple of reasons. Anthropologists have looked at this question, and they tell us that, well, where you have access to milk, where there are cows, people would drink milk because it was available and it was a good source of protein and calories to help people survive. And so we're milk cows. Well, that's Scandinavia and Northern Europe. They didn't have cows in North and South America until the Europeans brought them over. So that helps to explain that, why it varies so much. Now, I personally am lactose intolerant, and so what that means for me is I don't have the enzyme so much to break down the lactose, and that causes bacteria in my gut to produce gas, and it makes me kind of musical. And it doesn't bother me so much, but when I'm driving with the family, I should probably roll the windows down. Now, as kind of a public service, I could either stop eating dairy products, but I really like cheese, and I love ice cream. And so I can take lactase tablets. They contain the enzyme to help break that down. I could also buy lactaid milk and ice cream where the lactose has been broken down. So there's a couple of ways of managing that. I'm of Indian descent, so it's not very common for Indians to consume a lot of dairy products in their diets, and so there's a lot of lactose intolerance. But we get by. We can manage with a little biochemistry. All right. This disaccharide is also of interest, but we're going to start with the monosaccharides first and then pull it together. So up here I have a monosaccharide. I better put the OHs on here. OH on there. Okay. This monosaccharide right here is alpha glucose. Alpha glucose. And this one right here is beta fructose. Now, this is alpha because this hydroxyl group's going down. This one's beta, it's going up. And then just identifying some things here. This right here is our anomeric carbon. So anomeric carbon atom. And we have one here as well. Anomeric carbon atoms, okay? And then numbering these. Well, this here is our first carbon atom, second, third, okay? And then here, as we number this one, this is a little bit different. Here we've got this group coming off here. So this right here is carbon number 1, then 2, then 3. And that's important when we think about the glycosidic linkage that's going to happen. We're going to join these two together. And when we join these two together, we're going to remove water right here. And so what I'm going to do here is I'm just going to take off the hydroxyl group here and a hydroxyl group here. I'm going to leave an oxygen in between. I'm going to go plus water like this. And we're going to join this together like that. Now this glycosidic linkage is coming off the first and the second carbon atoms here. So we're going to call this a 1-2 glycosidic linkage, and over here it's coming off of the alpha, and here it's coming off of the beta anomeric carbon. So this becomes alpha beta 1-2 glycosidic linkage. Now when we join these two molecules together, the glucose and the fructose like this, it has a fancy name. This one here is called sucrose. And sucrose is just the fancy biochemistry name for table sugar. And this molecule, as we take a look at these anomeric carbon atoms like this, they're joined together like this. And that means we don't have an aldehyde group available to open up. And so this is a non-reducing sugar. I can remember how to spell here. Non-reducing sugar. All right, sucrose. So that's table sugar. And you may have heard of fructose, okay, from fruit, and maybe even high fructose corn syrup. And you say, well, what's the deal with high fructose corn syrup? So high fructose corn syrup is made from corn, and they just take the sucrose from corn, and then they use some chemistry to break it into the fructose and the glucose. Right? So it's the same molecules in table sugar. So it doesn't really matter if you get your sucrose from sugar beets or from sugar cane or from corn. You end up with the exact same glucose and fructose. Now what makes high fructose corn syrup is they just change the balance. So if you just take sucrose, break this up, you're going to end up with a 50-50 mixture here. 50% glucose, 50% fructose. In high fructose corn syrup that they add to like soft drinks and such, they're going to make a little bit extra fructose, and so it'll be like 55% fructose and 45% glucose is all. And what they find is that Um, the high fructose corn syrup is preferable in the food industry anyway, because it's cheap. It's a lot cheaper to grow corn than sugar beets and sugar cane, and that's also because we have subsidies for corn in the United States. It is more stable. It has a longer shelf life if you use the high fructose corn syrup as a sweetener as opposed to sucrose. Yeah, and it's just plain cheaper. And so some people are concerned about the high fructose corn syrup as far as what are the health effects of this. And as it turns out, the science tells us there really is no difference, because molecularly they're the same. Whether or not you get your fructose from a beet or whether or not you get it from corn, it's the same molecule. Now, there does seem to be a link between drinking soft drinks and obesity and cardiovascular risk. And is that because of the high fructose corn syrup, or is that just because people that drink more soft drinks tend to have more obesity and such? So there isn't any science so far to back up the idea that high fructose corn syrup leads to these adverse health effects any more than would getting your fructose from your sugar beets or from your sugar cane at this point. All right, there you go, the biochemistry here of the disaccharide sucrose.